But we're going to put all this back together here in a second because we want to figure out how much current is passing through each resistor. So we now know that we have a total current of 149.5. So leaving the voltage source, IT equals 149.5 milliamps. Now in series, we know that the amount of current going through a series circuit is equal at all points. So that means that the amount of current going into this resistor has got to be equal to the amount of current coming out of it. Since it's in a series one path, there's only one way for the current to flow. So we also know that the current coming through here would also be equivalent to 149.5 milliamps. But what happens here? So if we reconstruct our circuit back to its original, we know what's going to happen is that when this 149.5 milliamps reaches this node, it's going to go in two different branches. Part of it's going to go through this resistor, and part of it's going to go through this resistor. So now we're going to forget the rest of this equation exists. We're just going to look at this portion right here. And we know that the current flow is going to be proportional to the resistance values. Now, the lower the resistance, the more current's going to pass through. The higher the resistance, the less current's going to pass through. So what we know is this is going to be divided up between these two circuits, but there's going to be more current on this side than there is on this side. So the formula for the current divider says that the current flowing through a specific resistor, we're going to choose R2 as the resistor we're looking for, is going to be equal to the total resistance of that part of the circuit. So just this part right here, divided by the resistor that we have in question. So in this case, we're going to call this R2. And then we're going to multiply that, hopefully this is still on the screen, by the total current coming into that portion. So in this case, we had 149.5 coming into this point. So we're going to multiply this by that value. Looking at my lines, I think I ran out of room. So we'll say R2 equals RT of this portion. I want to give this a C node because I want to distinguish this RT from the total resistance of these two from the whole entire circuit. So what I'm going to do is I'm going to call this RT between C and B. So just this portion right here. Divided by the resistance of R2, because this is the one we're curious about, how much current's going to flow through it. I think I made the same mistake I did earlier. We're going to multiply that by the total current coming into C to B. So let's see what that looks like. So we plug that in. We're going to do it on this side, so hopefully you'll be able to see it. I think that's going off the screen. All right, we need the total resistance of these two together. Shouldn't have erased it. Afterthought. So 1 over 22 plus 1 over 33. I think it was 13.5. So the total resistance of this section, we're going to call that RT from C to B. Total resistance from node C to B is going to be equal to this, which we just now determined is 13.2 ohms of resistance. So the total resistance between C and B is 13.2 ohms. So now we're going to put this value according to the equation there. So 13.2, let's leave this out, we'll get confused. And we're looking at this value here, so R2 is 22, and we're going to multiply that by the current coming into C, which in our case was 149.5 milliamps. which will give us 89. So the current passing through R2 is 89.7 milliamps. Now, to get the current passing through R3, since there's only two of them, we have a couple options here. We could replug the numbers in. So current passing through resistor 3 would be the total resistance again, which was 13.2, divided by the resistance value of R3, and then multiplied by the current coming in, which was 149.5. Or you could have just said that the total current passing through these two resistors has to be equal to that amount, so you could just do 149.5 minus 89.7. We're going to do it this way just to make sure the math comes out correct. And it says that it would be 59.8. So the total current passing through R3 is going to be 59.8 milliamps. And if we add those two values together, according to Kirchhoff's current law, they should be equal to the amount of current coming into that node, 149.5. So we've now determined the amount of current passing through each of these resistors. So through this resistor, because it was in the series, we had the full value. Current of R1 was 149.5 milliamps. That means that coming into node C was a total current of 149.5. It's split across these two because they're in parallel, proportional to the resistance value. And the divider rule says that we take the total current of this little section of the circuit. So we're just calling it the total resistance between C and B, which was 13.2. We plug that into the total resistance of this section divided by the resistor in question, multiplied by the amount of current coming into that node. So we have 89.7 milliamps coming through number 2 and 59.8 milliamps coming through resistor 3. Now we said earlier that the lower the resistor, the higher the current. The higher the resistor, the lower the current, so all this is coming out right. So that's how we find the amount of current flowing through any of the individual resistors.